Hello, everyone. Welcome to our final presentation on deep networks for steering angle prediction. An integral part of autonomous driving includes perception and prediction to do obstacle detection and lane keeping assist. Many projects use sensors such as LiDAR, but they can be very expensive and lacks robustness. A lower cost alternative is camera, which records streams of pictures. And we have many deep learning models such as ResNet, which can work very well as static feature extractors on images. However, they overlook the temporal relationship between the frames. The goal of this end-to-end steering prediction task is to accurately predict cars' dynamics, including steering wheel angles, speed, and torque at any given time, based solely on current and previous video frames. The data we have includes more than 30,000 images taken by dashcam while driving in various environments. One work that we took inspiration from is this paper by NVIDIA on deep steering, and we have re-implemented many features of their network structures.
The general approach to our model should be to predict steering angles in real time based on previous images gathered from a dashboard-mounted camera. Unlike other temporal prediction tasks, we only include context from prior frames, not future ones. These features are then passed through a recurrent neural network, which predicts steering wheel angle, vehicle speed, and steering wheel torque. There are three major novel components to our project, the first being spatio-temporal convolutions. In many well-known image models, such as ResNet, the ability to characterize frames is very difficult due to subtle pixel motions, and we demonstrated this in an interim report. Thus, we utilize temporal convolutions across numerous frames. The second component is convolutional LSTMs. The temporal information from the spatio-temporal convolutions is fed directly into LSTM, but needs to be transformed such that information between adjacent frames isn't lost. The convolutional LSTM is a method that determines the future state of a certain cell in the frame by the inputs and past states of its local neighbors through the use of a convolutional operator, specifically a 2D convolution. The last component is a regularization technique that emphasizes the wheel angle as this is the core component in our project. Additionally, from a frame-to-frame perspective, speed and torque are mostly consistent, but the steering wheel is not. The formula above, gamma, is a new hyperparameter we need to tune over.
Our model architecture is comprised of two subnetworks, one for extracting important features from the road imagery, and the other for predicting steering wheel angle, vehicle speed, and torque. Our feature extractor uses a sequence of 5 three-dimensional convolutional layers to extract spatial and temporal data. This is then fed through a convolutional LSTM and linear feature extractor, outputting 128 features. The prediction subnetwork takes in the output of the feature extracting subnetwork at each time point. These features are concatenated with three-dimensional predictions from the previous time steps and fed through a recurrent LSTM layer. The LSTM output, current 128 dimensional features, and three-dimensional previous predictions are all concatenated together and fed through a linear layer to produce the current time steps, steering, speed, and torque prediction. We experimented with different network structures, and our best performing architecture was a convolutional LSTM paired with an LSTM predictor as described previously. The loss function we used in our problem is root mean squared error between our prediction and true labels. Training took around 60 minutes per epoch, and training loss decreases as a general trend, but we observed more fluctuation in validation losses. Nevertheless, the average deviated degree distance between predictions and labels are within a reasonable range of 3.7 degrees after 50 epochs of training. To visualize the loss and accuracy numbers better, we checked human steering angle with our model prediction over a 40-frame clip of daylight driving. The red line is the angle our model outputs, and the blue line is the true label. In this clip, you may observe that our model understeers, but it generally follows the correct direction of travel.
After initial training, we performed some ablation analysis by replacing the conv-LSTM with a plain LSTM. As you can see, the conv-LSTM shown on the left is able to reach a lower loss than the plain one shown on the right. This is evidence that we've effectively combined spatial and temporal information through the use of spatial recurrence. A significant challenge we ran into originated from the dataset. This dataset had a wide variety of driving images, and some images could be too bright or dark to realistically draw features from. We also believe that this wide variation resulted in training and validation performance discrepancies, since the split between training and test data could have resulted in two very different sets of imagery. So for future work, we considered performing data augmentation, like transforming the brightness, to remedy these issues and make our model more resilient to different driving conditions. Another architectural feature we'd like to add is skip connections, as seen in ResNet. This better allows for low-level features to be propagated through the model and influence the final prediction and performance. Thank you.